Okay, when you hear the words high tech, what pops into your head? You're probably thinking about gleaming robots, right? Or maybe supercomputers, artificial intelligence. But what if I told you that some of the most advanced, most absolutely critical technology in the world is just the air inside a room? So let's really think about this for a second. Picture a place that makes life-saving medicines, say for cancer. I mean, every single surface is perfectly sterile. Every process is measured down to the nanometer. In a world that is that controlled, what do you think the single biggest threat is? A power outage, maybe a tiny chemical impurity? What could it be? Well, the answer is kind of shocking in how simple it is. It's not some complex failure. It's us. Yeah, people. Every single person who walks into that super clean space is a potential disaster waiting to happen. In this high-stakes game, we are the ultimate wild card. And look, this isn't just a guess. The data here is just, wow, a full 75%. 3/4 of all contamination in these clean rooms comes directly from people. And you might be asking, why? Well, it's because the average person sheds something like 30 to 40,000 skin cells every single hour. We're breathing out aerosols. We're covered in microbes. From a manufacturing point of view, we are basically just walking, talking particle generators. Seriously, everything else combined doesn't even come close. So what this all boils down to is something really important. Protecting the product is protecting the patient. Think about it. A single stray bacterium getting into a vial of medicine could be absolutely catastrophic for someone. And to stop that from ever happening, the entire industry has to wage this constant, high-tech war against an enemy you can't even see: contamination. Okay, so that brings us right into our first section, the invisible threat. We're going to get into what this enemy is actually made of and the incredible engineering that's been designed to fight it. So what's the main weapon in this war? Well, it's actually something we're all familiar with, but it's been completely redesigned for a mission-critical job: HVAC. Yeah, heating, ventilation, and air conditioning. But forget everything you know about your home AC. This isn't about being comfortable. In the world of pharmaceuticals, HVAC has one single purpose: to build and defend a fortress of perfectly controlled, perfectly clean air. And when I say control, I mean everything is controlled. These systems are constantly managing four key things. First, temperature and humidity. And again, not for comfort, it's all about making sure the medicine stays stable and doesn't break down. Then you have particulate control, which is the direct fight against all that dust and those microbes we talked about. And finally, air pressure. Oh, this is the real masterstroke. It literally creates invisible walls of air, making sure that air always flows from the super clean areas out to the less clean areas, and never ever the other way around. So how on earth does one system do all of that? Well, it's time to pop the hood and take a look. Let's go inside the air machine. Right, so this is basically the command center. The absolute heart of the entire operation is called the Air Handling Unit, or AHU for short. And honestly, you shouldn't think of it like your furnace at home. It's way more like the life support system on a spaceship. It pulls in regular air, puts it through this incredibly intense conditioning process, and then sends that perfect air out to the clean rooms. And inside that AHU, the air goes on a real journey. It's basically a 5-step transformation. First, it hits some preliminary air filters to get rid of the big stuff. Then it goes to heating and cooling coils that work together to nail the temperature to an exact setting, often within a single degree. After that, humidification systems get the moisture level just right. And finally, a huge supply fan shoves all of that perfectly conditioned air out into the facility to do its job. Now, in that whole process, there's one component that's the real hero of the story. It is the final guardian at the gate, the absolute last line of defense against any microscopic threats. So let's do a deep dive on this incredible piece of tech, the HEPA filter. The backstory here is just wild. HEPA filters weren't invented for hospitals or anything like that. They were actually developed for the Manhattan Project back in the 1950s. Their original job? To capture radioactive particles out of the air in nuclear facilities. I mean, even its original name, high-efficiency particulate arrestor, sounds intense, right? It tells you just how serious its mission was from day one. So what exactly does high efficiency mean? It means this number, a bare minimum performance of 99.97%. That's the standard. And that number is the key to the whole definition. A real HEPA filter has to be able to remove at least 99.97% of all the airborne particles that are exactly 0.3 microns in size. Now, to give you some perspective on how tiny that is, a single human hair is about 300 times thicker than that. So we're talking about a level of filtration that is just almost unbelievably good. Okay, now this is where the science gets really interesting and kind of weird. You'd automatically think that the smaller a particle is, the harder it is to catch, right? Well, not quite. See, really big particles just get stuck easily. And the teeniest particles are so light, they basically just bounce around like crazy until they eventually hit a filter fiber. But there's this weird middle ground, right around 0.3 microns. They call it the most penetrating particle size, where the particles are too big to bounce around much, but too small to be easily caught. That's the filter's absolute weakest point. So by testing and certifying the filter at its worst possible performance, you guarantee it's even better at catching everything bigger and smaller. It's brilliant. So having the world's best filter is great, but that's only half the battle. You have to use it the right way. That brings us to our final section, the rules of clean. This shows a really critical idea perfectly. It's not just about having clean air, it's about how that air moves. On the left, you see turbulent airflow. That's kind of like your AC at home. It just blows clean air around and mixes it in, which dilutes the dirty stuff. But for the most important areas, you need what's on the right, unidirectional airflow. Just think of it like a giant invisible piston of pure air that's constantly moving in one direction, from the ceiling to the floor. It doesn't mix with anything. It physically shoves any contaminants down and out of the room. It's like a constant cleaning process that never stops. So who makes up these rules? Who decides what's clean enough? Well, it's not just one group. It's a whole network of global and national organizations. You've got ISO, which sets the basic classification system. Then you have the FDA, which enforces those rules for any medicine sold in the US. And then you have broader guidelines like Good Manufacturing Practice, or GMP, and rules from the World Health Organization that really set a global standard for safety. And believe me, these rules are incredibly specific. Just take a look at this. In a top-tier grade 5 critical area, this is where the medicine is actually exposed to the air, the limit for particles of a certain size is only about 3,500 per cubic meter of air, okay? Now compare that to a grade 8 support area, maybe like a hallway just outside. The limit there, it's over 3.5 million. That is 1,000 times dirtier, all within the same building. The difference is just staggering. And you can't just set the stuff up and walk away. It's not a set it and forget it kind of thing. A clean room is really like a living, breathing system. It has to be tested and revalidated constantly. I mean, technicians are always in there with particle counters and doing smoke studies to prove with cold, hard data that the system is working perfectly every single day. There is absolutely zero room for error. And that really brings us right back to where we started this whole conversation. You know, we live in a world that's just obsessed with technology we can see and touch. You know, faster computer chips, smarter AI, slick new phones. But it makes you wonder, doesn't it? Could it be that the most important innovation protecting all of our health is the one that we can't see or feel or touch at all? The one that's literally all around us right now, the air itself.